Hello everyone and welcome to another video. Today I'd like to talk about a concept that's very useful in controls and systems engineering, and this is the idea of DC gain. The easiest way to explain DC gain is just to think about having some kind of system, and the system has inputs, maybe let's call them R of t, and it has outputs, let's call it Y of t. Okay, and all DC gain is talking about here is if you put in a constant input, let's say a step of magnitude A, right? The response of the system is going to look something like this. You know, there will be some initial transients or whatever, and then it will settle out to some other value, and it's going to come to some steady state value. Okay, so all DC gain is talking about here is basically after you let the transients die away, if you put in a step of magnitude A, what is the final value that this thing goes to here? So in other words, let's just quickly define this. Maybe DC gain is the ratio of the steady state output over the, I guess, steady input, or DC input, right? Right? Which I guess you can kind of see why it gets its name here, right? DC, you know, this one comes from direct current versus AC for alternating current here, right? But DC power is you just put in a constant voltage into this system here. And now what we want to see is after the transients die away, what is the constant whatever that comes out? And we're going to see in a second that it doesn't have to be a voltage here, right? The units don't even have to match. All DC gain is talking about is the ratio of what you get out over what you get in here. So again, we can write this down here. So DC gain, maybe mathematically, this is just going to be the steady state output, which really is the limit as t goes to infinity here of the output, right? Over, in this case, magnitude A, right? Because that's the magnitude of the input that we put in. So again, it's just steady output over the steady input here, right? So I guess the other way you can think about this is just Y steady state over the magnitude of the input A. Okay, so the DC gain is useful because what it does, as you can see, is it tells you how the system is going to behave at steady state here, right, as time goes to infinity. So in some scenarios, you might want this DC gain to be, for example, 1. So let's look at a quick example here, right? Maybe like cruise control. All right, so let's say you've got a cruise control of your car here. So your car here has some, let's call it plant dynamics, in the sense that when you put a throttle setting, right, that results in some kind of velocity, right? And the velocity, maybe let's say we'll measure this in miles per hour, right? And the way the cruise control works here is that you compare how fast you're actually going, right? That's the velocity, with some V desired, also measured in maybe miles per hour, right? And that generates some kind of error signal, and then you have some kind of a controller, which is in this case your cruise controller. And this will be in charge of actuating the gas here. And hopefully what you would like at the end of the day here, right, is that when the operator here, when you as the driver specify some kind of desired velocity, eventually the car will reach that velocity. So maybe to use green like we were doing earlier, right? You come here and you say you're cruising along at, I don't know, maybe let's start it like this, something like this. You're cruising along at 55 miles an hour and you bump this up and you want to go to now 60 miles an hour, right? Well, what's the output going to do here, right? So you were cruising along fine and happy here at around 55 miles an hour. You command this thing to go faster, 60 miles an hour. The car is going to have to accelerate. Maybe it overshoots a little. Maybe it does something like this. But eventually, if you did your job right as a control engineer, the car would eventually be going 60 miles an hour in response to a commanded 60 mile an hour range here. So in this case, right, the DC gain you want is you would want 60 over 60, or you would want this thing to have a unity DC gain, or a DC gain of 1. So if you designed your controller right, this whole system from input to output should have a DC gain of 1, right? But you know, it doesn't have to be 1. There are many scenarios where you might have a system where the DC gain is not 1. So let's look at another example here. Maybe let me erase this down here. You know, how about like an airplane engine? Right? Let's say you've got some Cessna here or some small aircraft that has an engine. Right? And again, maybe what you input to this engine here is a throttle setting. And maybe this is like a fraction or a percentage between 0 and 100, right? And when you set the throttle, what ends up coming out of this is a propeller, like an angular velocity of the prop, maybe measured in RPM, right? Now, in this case, you can kind of see that for this system here, for this plant here, or this block here, or this model here, there's actually no reason you would expect a DC gain of 1 here, right? If you put a throttle setting here of something like, again, maybe you go from 0 throttle up to half throttle, up to 50%, right? Again, coming out the other side here is the engine's not spinning, but then the propeller's going to start spinning, and again, maybe it does something like this. But I don't want this to go to 50 RPM. I hope it's something a lot bigger, like, I don't know, 2,000 RPM, right? Or something like that. So in this case, the DC gain of this system would be the steady value of 2,000 all over 50, right? So again, there's no reason for it to be 1 in this case. So again, we just want to talk a little bit about how to get a feel of what DC gain is, right? It just tells you how the system behaves at steady state in response to a step input, right? Or a constant DC input. So with that in mind, maybe what we can do here is let's see if there's a way we can somehow mathematically relate the DC gain of the system to its transfer function. So let's take a gander at that now. So I'm going to just erase all this to give ourselves a little bit more room to work. Okay, so let's take a look at that now. Okay, so we remember here that the DC gain is basically your steady state output over the magnitude of your input, which we said was a step of magnitude A, right? Okay, so now why don't we go ahead and compute what is Y steady state, okay? So let's say compute Y steady state, okay? So Y steady state, okay? So that's basically its limit as time goes to infinity of Y of t, right? Okay, let's go ahead and assume that this system is stable and that Y of t is bounded here. So actually, maybe instead of note, let's just say assume Y of t is bounded. Right? What that's going to allow us to do here is we can now apply final value theorem. Right? So final value theorem, if you haven't had a chance, you remember we actually talked about final value theorem in our previous video over here. So maybe take a moment if you haven't watched that video already to just go pop back over there and brush up on final value theorem, because we saw what final value theorem is going to allow us to do here is final value theorem said that this limit as t goes to infinity of Y of t, right? This was limit as s goes to 0 of s times y of s, right? It was the behavior of the system in the Laplace domain related to the behavior of the steady state behavior of the system in the time domain here, right? So what we have here is I can replace this thing with limit as s goes to 0 of s times y of s, right? And now maybe let's draw our picture here, right? Our picture here was you have some system, right? And we were going to model this thing as a transfer function for now, so g of s. So this thing has inputs, in our case, I think we called it r of s. Maybe we should use big R, right? And this thing has output y of s, right? So from our transfer function, we know that the output of the system, it's the transfer function times the input of the system. Right? Okay, so let's substitute that in. So now we have limit as s goes to 0 of s times g of s times r of s. Okay? Now, with all of this DC gain discussion, what is this input here? The input to the system is, since we're talking about DC gain, it's a DC value. In other words, it's a step of magnitude A, right? So in other words, right, r of t is A times the unit step times 1 of t, right? If you want to think about it that way. Or the more convenient thing to think about this is, let's think about this in the Laplace domain here, because I need R of S, not R of T. So we're also going to make a quick note here that R of S, it's a step, right, of magnitude A. So the way you write that in Laplace domain, that's A over S like that, right? Great, substitute that in here, and we end up with, here we got limit as S goes to 0 of S G of S times A over S. So these S's cancel here, and now I can take the limit as S goes to 0, and we end up with, well, that just ends up being G 0, right? So anywhere you see S, right, in the transfer function, you are just going to replace it with 0 at this limit here. So we have this. We have the y steady state of the system here, oops, times A. Okay, right? Great, box this up. Okay, so that's the steady state output of any system in response to a step of magnitude A. Now what we can do here is let's plug this into our definition of DC gain here, right? So if you remember, right, we said DC gain of your system, right, was just y steady state over the magnitude of the input over A. So great, plug in y steady state into this here. So we end up with G of 0 times A all over A. The A's cancel here, and we end up with our result that we're looking for here is that this is very fascinating here, right? The DC gain of your system is just the transfer function with S equal to 0. So you take your transfer function, any transfer function, I don't care if it's first, second, third, fourth, 100th order system, everywhere you see an S, just jam in a 0 instead. Whatever you're left over with, that is the DC gain of your system here, right? Great, let's take this one step further and see how is the DC gain now maybe related to, say, steady state error here. So let's take a look here. Maybe what I'll do is, let's leave the picture up here and maybe erase some of this. Okay. And you know what? I'm not sure if I really like this concept, the nomenclature, the moniker of steady state error, because in some cases it's not really, it's a little bit misleading, but let's just use it to be consistent with everybody else in the controls world. Talk about steady state error, ERR. Okay, let's think about how this is related here. Okay, so what typically here is how steady state error here is. Maybe we should write this out here. So E steady state, right? This is basically the difference in the steady output to the steady input here. That tells you how far away or is the system tracking or not tracking the input here, okay? So in other words, the difference here between the input at steady state, right? The input at steady state is A, and the output at steady state was Y steady state. Right? So this is basically the difference between input and output, right, at steady state. That sort of is this concept of steady state error. So again, if this was a cruise control of your car, that makes perfectly good sense, right? Because the input would be a specified velocity here, and the output is the actual velocity. So if the two don't match up, yeah, I guess you would call that an error, right? But if this system here was, say again, that airplane motor here, the input is the throttle setting, and the output is the propeller speed. Again, this is why error doesn't seem to make sense, because I would never expect those two things to be the same. Heck, the units don't even match here, right? So in some cases, this matters, some cases this doesn't. But let's take this one step further, okay? So, all right, let's put this in. What did we say was the steady state error for this system here, right? So if you remember our previous discussion we just had here, is we said y steady state, that was just G0 times A. Right? Okay, so just factoring this thing out here, we can see that we can write this thing as 1 minus G0 times A here, right? So here's the steady state error of your system, okay? So again, if you're in a situation where it's like a cruise control or something where you want 0 steady state error, well, and again, this is maybe what we should say is, I forgot, one thing that we should say is, this is the error, or I guess the steady state error in response to a step. of magnitude A. Magnitude A. We're going to take a look at ramps a little bit later in a different lecture or other types of input. But anyway, this is what we end up with. So you can see that if you want zero steady state error, you better make sure that your system has unity gain, has a DC gain of unity here, right? So again, G0, this was our DC gain, right? Okay, great. Let's see here. Okay, let's maybe look at an example real quick here so we can maybe wrap our heads around this a little bit more. So our example that I like to do is let's use our good old friend, the mass spring damper, the same thing we've been using, because I think everyone has a good feel for this system here and how it should behave, and it allows us to do what I like to call the engineering duh check to make sure that everything seems reasonable. Okay, so here's the system, right? Spring damper, we're putting a force on it to the right is positive, and we're measuring the position deflection here, okay? So to save everyone the boringness here of deriving this, you guys have seen this many times here, right? But the transfer function is given by G of S, right, is the output, which we said was X, right, over the input, U. Right, you could write this thing as if you do the equations of motion, take the Laplace transform, do all that stuff, you can write this thing like such. It's a second order system. Okay, and now to make life easier, let's choose a couple of constants here. Let's just say M is 2 kilograms, B is 1/10, and K is 5. Okay, so what I want to do now is let's go over to Mathematica here and actually compute things like the steady state position here, the DC gain, the steady state error, and just make sure all of this seems reasonable. Again, what you would expect this thing to be, since you already have a good feel for this is a pretty underdamped system here, so I would expect the response of this system to be very oscillatory. And now the question is, where does this oscillation die out to? Does it actually track the input? All of these kind of good stuff. So tell you what, let's jump over to Mathematica here and finish out this example looking at the DC gain of the system. All right, so here we are in Mathematica. Let's go ahead and explore the DC gain of the mass spring damper system, right? Okay, so let's go ahead and put in our transfer function here. I think we said that this thing was what? It was 1 over m over s squared plus b over ms plus k over m, right? That was our transfer function. Okay, and now I think what we said was no, actually, you know what? We got rid of some of these constants, right? We said the mass was 2, the damping ratio was 1/10 here, and the spring constant was 5. Here, let's do this to make our lives a little bit easier with the calculations. Okay, so now what we need to do is, let's just do this by brute force. Let's say we didn't know the trick about just plugging in s equal to 0 everywhere and try to compute the DC gain by hand, okay? So the first thing we need to do is compute or get the response of the system to a step input of magnitude A. Right? So that means we are looking for y of s is what? It's g of s times a over s, right? That's how we get the input, or sorry, that's how we get the output here. And sorry, I don't think it was x, y. We used x was the output variable we care about, right? So let's call this x, and maybe let's call it x step, right? Because this is the response to a step. And this was g of s times a over s. Right? There we are. Okay, so now what we can do here is let's convert this back in the time domain here. So get the response in the time domain, right? So to do that, we are going to inverse Laplace transform this puppy from the s to the time domain. There we go, and maybe let's make this thing, let's call this maybe lowercase x step in the time domain. Great, there we are. Okay, so now what we can do here is take the limit of this thing as time goes to infinity to figure out the steady state value here, right? So to get the steady state output, take limit as time goes to infinity of x of t, right? That's what we're looking for, right? This here is x steady state, right? Okay, so let's just do that in Mathematica here. So what do we have? We have limit as x step of t as t goes to infinity. Whoops, come on, I can type. Infinity. Okay, there we go. So it's a over 5. Okay, so now what we can do here is let's get the DC gain of the system, right? So the DC gain was defined as, right, we talked about this earlier, right? We said this was y steady state all over the magnitude of the input, which was input A here. Oh, sorry, I keep using y. In this case, it's x, right? That's what we're looking for. So it's basically, oh, sorry, I should assign this thing to a variable. This is x steady state, right? Okay, so we end up with x steady state over a, and yay, look at that. It's 1/5 here, okay? So what this means here is that the system attenuates the input by a factor of 5 here, right? So let's just verify that here. So let's just make a little note here. So the takeaway is that the system attenuates the input by a factor of 5. So for example, if we put in an input of, say, let's just say a is equal to 5 here, the output of steady state we should get is just x is equal to 1, right? So we can, let's plot this, how about? So let's plot x step of t, and let's put in an input of 5 here, right? So now a is a magnitude of 5. Let's plot this thing from t equals 0 to 200 here, and shift enter that. And there you go. Oh, sorry, it looks like it's cutting things off. Let me change the plot range of this thing so it doesn't cut anything off. There we go. So you input a step input of, in this case, it would be 5 newtons, right, or 5 force units, and the output is the block goes to 1 meter, right? That's what you can see right here. It oscillates a whole lot, but here at the end of the day, it comes down to 1, right? So it does attenuate this by 1. Now, let's just verify our DC gain calculation. Verify our DC gain calculation with G0, right? That's the other way we could get the DC gain here. So apparently, there you go. If you take our transfer function and plug in, everywhere you see an S, you plug in a 0, you get 1/5 here, just like we saw earlier. So that is awesome. That's working well. Maybe let's do one last thing here and investigate how about the steady state error, right? And maybe let's put this word error in quotes, because you're going to see in a second, again, this is what I'm saying. I don't really like the nomenclature in all situations here. So on the board here, what we showed was the error was this, right? So in our case, what do we have? This is 1 minus 1/5, right? Because that was the DC gain. So the DC gain was this G0 term here, right? And our input was a step of magnitude 5, actually. Right? So I think if you crunch all these numbers, you get 4, right? Which makes sense here, because what that's basically telling you here is you put in an input of 5, which if we come back to this graph, unfortunately, I guess it doesn't show 5 way up here, but the output of the system is 1. So the difference between 5 and 1 is 4. And again, this is why this doesn't really make any sense, because I can't even tell you the units of what this is here, right? For what? We input a force on the block, and we got out a position in terms of meters. So in this case, the error is just 4, but again, that's kind of meaningless, and it's kind of just an academic exercise at this point. So, with that being said, I think this was a good discussion here. I just wanted to do a quick discussion here on DC gain, because we're going to use this here in what we're going to call time domain analysis of various systems coming up in a couple of future lectures. So, just to summarize here, what the DC gain of a system is it's just the ratio of the steady state output over the steady state input here. So if all you want to think about with DC gain is you put something into a system, eventually at the end of the day, what you get out of the system, right? Does the system amplify, attenuate, or just pass that signal through here? That's basically what the DC gain does. So I hope you enjoyed this video. I hope you'll join us on one of our future ones. If so, please go ahead and like and subscribe the video. It really helps me keep making these, and I hope to catch you at a future video. Talk to you later. Bye.